Dear students, let's continue our practice on mathematical analysis 1. So the next topic is second order linear differential equations with constant coefficients. So firstly, I want to give a definition of second order differential equation. This is a differential equation is written in general form f x, y, y prime, and y second order derivative is 0. So this is we call second order differential equation, where f is a function of the given arguments. So now we will move to the second order. We considered with you the first order differential equation. Now we will move to the second order differential equations. And now, if the differential equation can be resolved for the second derivative, y prime, it can be represented in the next form, implicit form. Y prime is f of x, y, and y second derivative, I mean, y prime here, double prime. So this one is y double prime equals to f, x, y, and y prime. So this is the second order differential equation. And now, in special cases, the function f of x, which is on the right side, may contain only one or two variables. Such kind of equation we call incomplete equations, and it includes 5 different types. First one is y double prime is f of x, just, or the next one is y prime double prime is f of y, or y double prime is f of y prime, or y double prime is f of x and y prime. Incomplete equations they are, yeah. And y double prime is f of y and y prime. We have 5 different types. And now in the case 1, when y double prime of f of x, this is first case, yeah. So here we can reduce by introducing new function p of x, such that y prime is p of x, and as a result we have p prime, yes, because this is double prime, so p prime of x, this is f of x. And solving this equation, we can find the function p of x, and then we'll solve this equation after finding p of x with respect to this p of x, and we will obtain a general solution of our given equation. In the second case, y double prime is f of y, yeah. Here we introduce again new function p of y now, and we can write y prime as p of y. So then we can write just y double prime as it is d of y prime over dx. Yes, this is the derivative of the first derivative from the first derivative. This is second derivative. And now y prime, it is p, so it will be just dp over dx. So now what we'll get here, However, we have p of, this is a function of p, this is function of y. So it will be now dp times dy over dy times dx. And we'll get here just dp over dy times p. dp over dy times p. So our equation now, dp over dy times p is f of y. Okay, so, and solving this equation, we find the function p of y, and then we find the solution of this one, and then we'll get our y. So case number 3, third case, this is this one, y double prime is f of y prime, yeah, y prime, yes. So now in this case, what we will get here? So again, we'll introduce the new function, which y prime is p of x, and we obtain the next equation. It will be y double prime is p prime or dp over dx, because p is depending on x, and it is equal to f of p, because y prime is p. So but now this is first order equation with separable variables p and x, integrating to both sides of our equation, we can find p of x and y, and then y of x. So the aim of this works is reducing second order linear, incomplete linear differential equations to first order linear differential equations. By this way, we can find easily for these 5 types of incomplete differential equations. This is not complete, this is incomplete differential equations. For this kind of equations, we can reduce the degree of our equation to the first order. Okay, so this is third case. Here we can write for the fourth case also. So fourth case is now y double prime is f x and y prime. So you can see by substituting we can reduce. Here also we'll substitute y prime as p of x, and then we will get p prime we have, and it is f x and p. If you put so, by integrating we can find here p of x. This is also separable variables. So, and then we can find y of x, putting here p of x. One more time integrate, and we'll get y of x. Okay, and for case number 5, this is also similar. It's similar with the second case. Let me write here. So here we will we have y double prime is f y and y prime. So setting y prime is p of y, and I said this is similar with the second case, and we can write here just y double prime is dp over dy times p, and it's equals to f of y and p. So now we need to solve this equation, and after finding p of y, we can put here p of y and substitute, and then find our y. It will be first order differential equation. So this is they are 5 types of incomplete second order differential equations which can be reduced to the first order differential equation. And now we'll consider the second order linear differential equation, of course completely, and with constant coefficients. Let's firstly consider the second order homogeneous differential equations with constant coefficients. Okay, consider the differential equation y double prime plus py prime plus qy is 0. This is second order differential equation, homogeneous differential equation, of course, with constant coefficients. We called p and q coefficients of our equation. So for each of the equation, we can write so-called characteristic equations: k squared plus p times k and plus q. So this is we call characteristic equation. So where we will change our y to k. So, and the general solution of homogeneous differential equation depends on the roots of these characteristic quadratic equations: q squared plus pq plus q. And we have the next conditions. This is quadratic equation set. So, and the discriminant of this quadratic equation can be greater than 0. If discriminant greater than 0, then the roots of these characteristic equations are k1 and the k2, any distinct real numbers. So in this case, the general solution the general solution of our equation is y of x is c1 times e the power of k1x plus c2 e the power of k2x. We'll find from this equation. This is general solution when discriminant is greater than 0, whereas c1 and c2 are any arbitrary real numbers. And now we have the second case when discriminant is 0. Discriminant is 0. In this case, we have only unique root, and but it is unique root has order 2. Our root, this is repeated root, yeah. K1, it is repeated root. So and it has order 2. And the general solution of the differential equation has the next form. Y of x is, now we have same k. So it will be, that's why c1x plus c2 times e to the power of k1x. And k1, this is repeated root of our equation, quadratic equation. And in the third case, if discriminant is less than 0, what we'll get here? So we have complex roots. So it is k1 is any complex number alpha plus beta I, and the k2 is alpha minus beta I, conjugation to conjugated complex numbers. So, and the general solution in this case is y of x is e to the power of alpha x times c1 cosine beta x plus c2 sine beta x. This is general solution when discriminant less than 0. So we have these 3 types of our second order linear differential equation, homogeneous differential equation with constant coefficients. So let's consider the first example. Example number 1. Solve the differential equation y double prime minus 6y prime plus 5y is 0. Okay, so how to solve now this example? Here let's write characteristic equation. K squared minus 6k plus 5, it is 0. It is 0. And the roots of this equation are k1 is 5 and the k2 is 1. Here discriminant is greater than 0. So we have 2 distinct real roots. And the general solution of our equation will be y is c1. Look, the first case, so c1 times e to the power of k1 x plus c2 times e to the power of k2x. So here we have k1 is 1, so that's why it doesn't matter which one is first one and which one is second one. So c1 times e to the power of, let k1 is 5x and plus c2 e to the power of x. So this is general solution of our equation. And now let's consider the next example. Example number 2. Example number 2. So here we have find the general solution of equation. For example, y double prime minus 6y prime plus 9y is 0. And now let's write characteristic equation. K squared minus 6k. Y double prime will be k squared, y prime will be k, and 9y will be just 9 is 0. How to find it? Find roots. So this is, here discriminant is 0. However, it is the form k minus 3 squared is 0. And we have repeated root, k is 3. One root, yeah, of order 2. So the solution of this equation will be y of x is C1, you look the second case, C1x plus C2 times e to the power of, it is K1, K1x, to do the same with the definition. So now, this is C1x plus C2 times e to the power of K1, it is 3x. This is general solution of our equation. And now let's consider the next example, example number 3. So, solve differential equation, y double prime plus 4y prime plus 5y is 0. Okay, let's write characteristic equation for this differential equation, and we have k squared plus 4k plus 5 is 0. Let's find discriminant. Discriminant is minus, so it is negative 16 minus 20. So this is minus 4, which is less than 0. So this is third case, yeah. And k1 and k2 are minus 4 plus minus square root of minus 4 over 2. Or this is minus 4 is 2i squared, because I squared is minus 1. Remember, in complex numbers, I squared is minus 1. So it will be minus 4 plus minus 2i over 2, or so it is minus 2 and the plus minus I. Now, so k1 is, for example, k1 is minus 2 plus I, and the k2 is minus 2 minus I. In this case, the general solution is y of x is e to the power of alpha x c1 cosine beta x plus c2 sine beta x. So here alpha and beta is k1 was in the form alpha plus beta e, and the k2 is alpha minus beta I. So now look here, our alpha is minus 2 and our beta is 1, just 1. That's why here we have y of x is e to the power of minus 2x times c1 cosine x plus c2 sine x. This is general solution. And now let's consider the next one. So exercise number 4. Here we have the next equation. Solve the equation y double prime plus 25. Y is 0. So this is k squared plus 25 is 0. Yes? And hence we have k squared is minus 25. So now we can solve using complex numbers. It will be k1 is minus 5i and the k2 is 5i. So we can solve using complex numbers. And here the answer can be written in the next form. So here this is general form, it was general form, and in this case alpha is 0 and beta is 5. Beta is 5. So it will be now y of x is c1 times cosine 5x, because this is 0 and e to the power of 0 will be just 1. And plus c2 sine 5x. This is general solution of our second order homogeneous differential equation. And now let's consider second order linear non-homogeneous differential equations with constant variables. So let's write the form of non-homogeneous differential equations, second order. So it is y double prime plus py prime plus qy is f of x. This is non-homogeneous differential equations with the right side, and where p and q are constant numbers. It can be they can be real numbers or complex numbers. And for each equation, we can write the related homogeneous equations. So the homogeneous equations is y prime double prime plus py prime plus qy is 0. This is homogeneous equation, yeah. And now here we have theorem. Next theorem, the general solution of non-homogeneous. The general solution of non-homogeneous equation is the sum of general solution of related homogeneous equation. This is y0, general solution of related homogeneous equation, and a particular solution of the non-homogeneous equation. This is y prime. This is general solution of, let denote by 1, let denote by 2. This 2 homogeneous equation, and y prime is particular solution of general solution. It is particular solution of first equation. So, and this sum of this one it will be, yes. So the general solution of first equation, let denote by y, and it will be y0 plus y1. This is main theorem, and here we consider two methods of general solution of non-homogeneous differential equation. The first method is method of variations of constants. So we use such kind of method in the first order linear differential equations. So let the general solution of second order homogeneous, let's consider first method, method of variation of constants. So the general solution of second order homogeneous differential equation y0 is c1 y of x, not this y now, other, let denote by capital, y of x plus c2 y of 2x. Yes, this is general solution of second order homogeneous equation. And here, instead of constant c1 and c2, we'll consider arbitrary functions, respectively c1x and c2 of x. And we'll find these functions such as the solution y0 is c1 of x y1x plus c2 of x y2 of x. Okay, so now and we will find it with the, I mean here we need to find not y0, just y, let's write it y, and it will be solution of which is satisfied non-homogeneous equation with the right side f of x. This particular solution here. And we have here simultaneous of equation. The And we can determine C1 and C2 by the next system of two equations. So it will be now C1 prime x y1 x plus C2 prime x y2 x. This is 0. And the next one is, the next equation is C1 prime of x y1 prime of x plus C2 prime of x y2 prime of x is f of x. Using this system, we can find these unknown functions C1 and C2. This method we call method of variation of constants. We'll consider examples, and it will be more it will be clear for you. So now let's consider the second method of undetermined coefficients. Method of undetermined coefficients. This is second method. Coefficients. So here the right side f of x of a non-homogeneous differential equation can be often an exponential or polynomial or trigonometric function or combination of these three functions. In this case, we can consider the equation, and the solution of this equation using the method of undetermined coefficients. So here we have two class of functions in the right side. First class is f of x is polynomial Pn of x times e to the power of alpha x, exponential function. Polynomial and exponential function. And the second class is f of x, here trigonometric and polynomial and exponential function. We have Pn of x cosine beta x plus Qm of x, second polynomial, sine beta x, and times e to the power of alpha x. So we will find our f of x from these two classes. We don't have any other classes here. And in both cases, choice for a structure of the second particular solution should match the structure of the right side of the non-homogeneous equation. Now we'll consider only the first class of f of x, which is polynomial times exponential function. In this case, if the power alpha of the exponential function coincides with the root of the characteristic equation, the particular solution will contain the additional factor as x the power of s, where s is the order order of the root alpha in the characteristic equation. And now let's consider the first example here, exercise number 1. Solve the differential equation y double prime plus y is sine 2x. So let's do it this equation with the first method of variation of constants. Firstly, we solve the related homogeneous equation, which will be y double prime plus y is 0, and the roots of corresponding characteristic equation k squared plus 1 is 0 are k1 and 2 are plus minus I. So here the general solution of homogeneous equation is given by y0 of x. This is c1 cosine x from previous section, yeah, plus c2 sine x, because alpha is here 0 and beta is 1. Okay, so let's write this c1 and c2 as unknown functions. So y of x is now c1 of x cosine x plus c2 of x sine x. Okay, now using the method of variation of constants, what we have c1 prime of x cosine x plus c2 prime of x sine x is 0, yeah, and the second one is c1 prime x cosine x prime plus c2 prime x sine x prime. This is our f of x is sine 2x, sine 2x. Then we have the next equation. So it will be let's write here c1 prime of x cosine x and plus c2 prime of x sine x. This is 0, and here we have c1 prime of x minus sine and plus c2 prime of x cosine x is sine 2x, sine 2x. Okay, so we have the following system, and now we can express the derivative of c1 x, yeah, this is from first equation. It will be minus c2 prime x sine x over cosine x, yeah. So we determine our c1 prime x, and substituting this c1 prime x to the second equation, what we'll get here. So, and we need to find c2 prime of x also. So let's put it, and after putting, it is now plus because we have double minus. So put to the first here instead of c1. So c2 prime x sine square x over cosine x plus c2 prime x cosine x is sine 2x, and hence we have sine c2 prime x, it is sine let's do factor out, and sine square x over cosine x plus cosine x, and it is equals to sine 2x. And by this way we can find here sine to c2 prime x. So c2 prime x, it is, if we multiply here cosine x, we have in numerator 1, and it will be sine 2x times just cosine x. Okay, we got this c2 of x and c1 of x, yeah. And after putting instead of c2 of x our sine 2 of x and cosine 2 of x, our c1 of x now is they are cancelled, and we have here minus sine 2 of x times sine x, yeah. Yes. Okay, now find this c1. So this is prime. Integrate both sides of our equation. We'll get c1 of x is here we have now dx, yeah. So it will be d so sine sine 2x and sine x. This is minus, so sine square x cosine x, if we open the sine to x, yeah, dx, and we can write it in differential, so it will be integral is minus sine square x d sine x, and it will be now with 2, of course. Here we have 2, we forgot 2 here we have 2, minus 2 sine cube x over 3, and the plus any constant. To not confuse this constant, we need to write, for example, any other coefficient with a1, for example. And by the same way, we need to find c2. So our c2 now is, let me write answer here. It is minus 2 over third cosine cube x plus a2, the next coefficient. Now our answer, let me write here, it will be now y of x. However, y of x was c1 of x times cosine x plus c2 of x sine x. Now it is just we need to put this c1 and c2. We have c1 and c2, and these two coefficients we need to put here, and we'll get the corresponding answer for the general solution of our non-homogeneous equation. Just putting this c1 and c2 to this equation, and we'll get the general solution. And now let's consider the next example. Find the general solution of the equation. Example number 2. So here we have the following equation: y double prime plus y prime minus 6y is 36x. Okay, now here we will use the method of undetermined coefficients, and the right side of our equation, f of x, is in the form polynomial form, so just ax plus b, yeah, we have here. This is polynomial form, and now we'll look particular solution in this differential equation. As y1 will be, we will find our particular solution in the form ax plus b. They should be same with our right side, should be same. And now, so derivative of y1 is just a, and the second derivative is 0. Now let's substitute this into our differential equation, given differential equation, and we'll have here 0 plus, so y derivative it is a, and minus 6 ax plus b is 36. This is second method which we told earlier. So using this method we can find this particular solution. Again, one more time I'll repeat. So particular solution we'll find in form of right side. So this is polynomial form, that's why we will find like this ax plus b. And now let's simplify this expression, and we'll get here a minus 6a x minus 6b is 36 x. And now what can we deduce here? So minus 6a, if equating the corresponding coefficients, minus 6a is 36 here, yeah, and a minus 6b is 0, because this the zero term is a zero power term, it is 0 in right side, so they should be same. This is identity. And now from this system we'll get here that a is minus 6 and b is minus 1. So b is minus 1, and as a result we will get y1, the particular solution of our differential equation, has a form however a is minus 6 minus 6a minus 1. This is our particular solution. Now we need to find the general solution of the homogeneous differential equation, and then we can write our solution as y0 plus y1, where y1 is particular solution, y0 is general solution of homogeneous differential equation. Okay, now to find the general solution of homogeneous equation, we need to solve characteristic equation. Yeah, so homogeneous equation has a form y double prime plus y prime minus 6y is 0, and characteristic equation will be k squared plus k minus 6 is 0, and hence here discriminant is greater than 0, and roots are k1 is so minus 3, and the k2 is 2. Minus 3 and 2 we'll get. So then what we have here, so we found our k1 and k2, and hence discriminant is greater than 0. The general solution of related homogeneous equation is given by like this. So y0 will be now c1 times e to the power of k1x plus c2 times e to the power of k2x, or c1 times e to the power of minus 3x plus c2 times e to the power of 2x. This is general solution of homogeneous equation. And now the general solution here of the non-homogeneous given, yeah, non-homogeneous equation now is this one, this given equation. I mean, here we have the next solution, y, one more time, y0 plus y1, and it means y0 is c1 times e to the power of minus 3x plus c2 times e to the power of 2x, and plus particular solution, and particular solution is here minus 6x minus our particular solution is minus 6x. It is not a, sorry, it is x. we need to put these values to instead of a and b. So minus 6x and minus 1. So this is general solution of non-homogeneous differential equation, second order. And now let's solve the next equation and the next example. Example number 3 now. Solve the differential equation y double prime minus 5y prime plus 4y is e to the power of 4x. So we need to find the solution of this differential equation, non-homogeneous differential equation, second order. So here let's firstly begin with the homogeneous equation, corresponding homogeneous equation, y double prime minus 5y prime plus 4y is 0. So let's find the solution of this equation. To find it, we need to find the roots of characteristic equation, where k squared minus 5k plus 4 is 0. So a discriminant of this equation is greater than 0. So it means we have two distinct real solutions here, and they are k1 is 4 by Wiett's theorem, and k2 is 1 and 4 we'll get. So now our homogeneous solution of homogeneous equation now has a form y0. It is now c1 times e to the power of like previous example, 4x plus c2 times e to the power of x just. Okay, now there were c1 and c2 are constant numbers. And now find a particular solution of non-homogeneous differential equation. So the power of the exponential function on the right side is 4, and it's coincide with the root k1. Yeah, with the root k1. So therefore we need to look for a particular solution of the form y1 will be ax times e to the power of 4x. So it will be particular solution for our differential equation, and the derivative of y1 is a times e to the power of 4x plus 4ax e to the power of 4x. Or let's factor out e to the power of 4x, and we have a plus 4ax. So this is y1 prime. And now let's find the second order, because we need first, second order and first order. So why we need to find particular solution? So we need to put this particular solution to our given differential equation, and we can obtain our y from this one. So, and the form, again, the form of particular solution, it depends on our right side. If it is with e to the power of x, it will be with e to the power of x. And y second derivative, it will be so from this one we need to find. Yeah, now so it is a just a second. If derivative from this one, it will be so 4a plus 16 ax times e to the power of 4x plus so 4a e to the power of 4x. And now let's put, or can we simplify? Yeah, we can simplify, of course. E to the power of 4x factor out, and we have 8a plus 16ax. Okay, now let's put to our equation, and we'll get here e the power of 4x. This is form of particular solution, e the power of 4x. So 8, let's copy, plus 16ax minus 5y prime, where is y prime? Yeah, e the power of 4x, a plus 4ax, and plus 4a x e the power of 4x equals to e the power of 4x. And now we need to solve this equation. Okay, so what we'll get here after this one, if we open, so we can factor out e the power of 4x, and they are cancelled. We can divide by e the power of 4x, and then because it's not equal to 0 always, and now after opening we have 8a plus 16ax minus 5a minus 20ax plus 4ax, and it's equals to 1. Okay, now what we'll get here, 16 plus 4, they should be cancelled, they are cancelled, and we have here 3a is 1, or a is 1 over 3. So the hence we have y1 is, instead of a, 1 over 3, 1 over 3x e the power of 4x. This is particular solution of given second order differential equation, non-homogeneous. And now let's write the general solution. This is y0 plus y1, the solution of homogeneous equation and solution of particular. And now it will be now c1 times e the power of 4x plus c2 times e the power of x, and plus 1 over 3x times e the power of 4x. This is general solution of our second order non-homogeneous differential equation. So to solve such kind of examples, you need do more practices at home. These topics are not so easy, but if you do more examples, you can do easily and faster your examples. If you have any questions, you can contact with us in our discussion group, and the next time we'll continue our practice. Thank you for your attention.